Hello and welcome. My name is Aman Kumar and I work for Infineon Technologies, Dresden, Germany. The topic for today is pragmatic formal verification of sequential error detection and correction codes used in safety critical design. So ECC basically consists of two parts or two stages, the encoding and the decoding stage. The ECC that we are using in our project is a quad bit error detection and triple bit error correction ECC. So it's a quad tech ECC. And we also have a sequential version of it where we have sequentially pipelined encoding and decoding stages. On the encoder side, the data input is added with some or encoded with some redundant bits called as additional ECC bits. And the resulting code word is then, for example, written into the memory. From the memory, the code word goes into the ECC decoder, where the job of the ECC decoder is to check whether the data is correct and if there are no bit flips. If there are bit flips, then the job of the ECC decoder is to set the flags, the error flags, as well as correct the data if it's within the correctable range. Now, there could be some soft errors which may cause data corruptions, and these soft errors in memories can occur due to various reasons such as radiation errors, electrical glitches, or magnetic interferences. Now, the ECC that we have is having a data bit of 128 bits with a possibility to detect up to 4 bits of error, as I said. Therefore, the combination of bit errors is given by this formula mentioned here, and it's too huge for any formal verification tool. As a safety critical design, it's very important to verify all possible combinations of data input in order to make sure that we comply with the ISO 26262 guidelines. Now, to overcome such a problem and sign off the design with more confidence and reasonable proof time, we came up with a pragmatic formal verification approach for ECCs which are complex in nature, where we talk about several complexity reduction techniques and know-hows that we learned during the course of the verification. The very first thing that we did was introducing bit errors using the precondition in the property. So what we did is we removed the memory and instead added the possibility of introducing bit errors using the precondition. On the other hand, we also looked more into the details of the ECC decoder, and we found that there are three major blocks: the syndrome generator, the error detection, and the error correction block. The syndrome generator, the output from the syndrome generator is fed into the error detection and correction blocks, which are mostly responsible for setting the error flags as well as correcting the data. And when we looked into the details of the syndrome generator, we found two very interesting arguments. The first one was if there is no error introduced in the code word, this implies that the syndrome output from the syndrome generator is always a null vector. So if CWI here is equal to the CWO, then the syndrome output is always equal to 0. On the other hand, we also found that the syndrome generator in itself is a linear function, which means that the syndrome output is independent of the data input. Now, by linear function, what I mean is it follows the algebraic linear function, which is basically a function f is called as linear if f of x plus f of y is always equal to f of x plus y. That is, f preserves the addition operation. And once we prove this using the properties, we could make sure that the output from the syndrome generator is independent of data input. So instead of writing a property where we have randomized data input, basically for any possible value, we take a fixed random value and only prove the property for that fixed value. So for example, if you want to detect multi-bit error detection, which is 4 bits of error detection, we say that the data I on the antecedent is fixed to a certain value. And then we introduce 4 bits of error between code word output and code word input. And on the consequence side, we check that the error 4 flag was set and all other error flags were set to low. So this reduced the complexity way better than the original problem, and we could prove this property within reasonable proof runtime. Now, as I said, we also had a sequential version of the ECC where we had sequentially pipeline encoding and decoding stages, as you can see here, and we also have some control bits. For example, encoder start I and decoder start I. We have clocks and reset as well. And if you see in the timing diagram here, We have data input, FF, for example, here. After 4 clock cycles, we get the code word output, which is then fed into the ECC decoder, and with additional 3 clock cycles, we get the data output from the ECC decoder. So it's taking a lot of time to really check the ECC decoder. And this means that the properties that we used using this linearity approach also failed or gave up after 120 hours of proof runtime. So we had to look into further possibilities, and the next thing was to prepare a reduced latency model. If you see from the timing diagram, it seems that the encoder has a longer latency here. And the idea was that we prepare a cycle inaccurate model of the encoder that calculates the ECC basically in the same clock cycle. So if you see here, we have the data input, and then we have the ECC gen function, which is a cycle inaccurate model, which will give the code word output in the same clock cycle as we feed in the data. But we compare the outputs at the end of the code word that we get out of the RTL, and we check that both of these values are same. And the next stage for the properties itself, we use the generator function instead of the RTL output. So this reduces the latency and also helps the tool to converge faster on the proof runtime. Even by using the reduced latency model, it was taking a longer runtime for the tool to prove the properties, and we investigated further and figured out an induction-based proof mechanism. So induction-based method is basically to check if a design, if it's in a random good state, whether it will be in a good state at the next clock cycle or not. And modern EDA tools such as Jasper Gold provides SST trace, which is state space tunneling trace, that gives hints for helper assertions, which we can write in order to converge the target property much faster. So for example, if we have a property T which is not converging, we generate the SST trace from Jasper. And if there is no trace existing, then probably there is no helper assertion which we can write to converge the property faster. On the other hand, if we have a SST trace, we can debug the trace, and based on the trace, which is a normal counter example, we can write helper assertions and then prove those helper assertions. Once these helper assertions are proved, they will be implicitly assumed by the tool. And then this will help the target property T to prove much more faster, considering the helper assertion that we provided. So in our case, the SST trace shows 2 missing constraints. The first one is here, where you can see that the error correction state comes even before the idle state, which is wrong. On the other hand, we have another constraint, missing constraint, where we can see that the decoding starts even before the encoding is finished. So for example, we have encoder start high here, and just after 1 clock cycle, we see that the decoder start I is also high, which is wrong because the encoding has not yet finished. So once we added these 2 missing constraints, this helped to prove the properties within 24 hours of proof runtime, and we also unveiled several bugs that were fixed before the tape out. Thanks a lot for listening.